So with respect to the stream, as I sent out an email, I learned that I inadvertently captured your audio on the stream last time, which I had not intended to do. However, I think it might actually work out better that way because then the questions are recorded faithfully and you get the full class experience, and those who are listening at home can participate as well. So if anyone has concerns about me doing that, please let me know and I can adapt accordingly. I haven't heard from anybody, so I think so far that means that folks are okay with it. If not, please let me know. All right, starting the screen share for you guys, which is the part that's actually being captured. All right, can you see my purple web page? Excellent. So this morning I got a chance to put up the homework portal. It is now live. I'm going to make a video demonstrating it because I didn't want to spend too much time in class doing that. But if you wanted to play with it on your own, you're welcome to do so. The idea of your first homework, which is homework 0, that's not due for a couple weeks. 9/7 is when that's due. So the idea is to give you practice with the system. And if you go through the first homework 0, you get 3 points extra credit for doing it. So it's just to make sure everybody can use it. I'm going to click on the link here just to show you the opening screen. And it wants your last name and your 8-digit Iowa ID. So if you don't know your ID number by heart by now, you will at the end of the semester from having to enter it. With respect to your last name, it is the last name that Maui thinks you have. So if you use 2 last names with a space, that's what you should type. If you use a hyphenated last name, that's what you should type. If that's a last name that you don't want to use for whatever reason, let me know and I can fix it after this homework is done, but that's what it should be. So once you are inside, you'll get a chance to practice answering questions which are just about the syllabus, and if you do so, you get 3 points of extra credit. The reason that the extra credit should matter is something I didn't get a chance to talk about last time. I have tried in planning this semester to walk the line between encouraging accountability and also trying to be flexible. In previous semesters, the policy that I had was that any homework assignment that was submitted late had 3 points docked. Because I know that you guys are really busy and you have a lot of competing demands. And I also know that things that have hard deadlines get done and things that have soft deadlines get pushed. And so I wanted to put this work into the hard deadline, make it a priority category, and having a penalty of points lost was my way of doing that. Last semester, when everything went crazy in March, I abandoned that policy of late points, and I ran into folks who ended up putting things off to the last minute and got themselves into a bit of a pickle trying to get everything done. So I don't want to encourage that either. So the compromise that I settled on for this semester is a penalty of 1 point for late work. So there's at least something to motivate you to keep up that's external instead of just internal motivation. However, if you do the extra credit homework to get used to the system, that's like saying you can be late 3 times without penalty. So I think that's hopefully a reasonable compromise on that. So I will post the video showing you how to use the system. You can watch the video and do it along with me. It will take a good 2 minutes of your life. Like, it's not a real homework, it's just questions about the syllabus. Those of you who have been in my classes before, it's the exact same system you already know, so it will take you even less than 2 minutes. So I will let you know when that video is posted, and if you can take a chance to do that sometime in the next week and a half, that will help. If you are new to the class, I've been tracking Maui to see if anybody has added, trying to catch all the late ads. If you've added as of this morning, I've got you in there. If there's anybody who hasn't officially added who plans to add, please let me know so that I can add you myself. All right, so that's all the logistics stuff that I can think of. Oh wait, one more thing. Just to point out, the video that I recorded from class on Tuesday is posted on Tuesday's date right here on the website, and I'll do the same thing for each day. So so each class period will have at least one video, and sometimes two if I split it for different topics for that kind of thing. Okay, I hear a TV. Say, hang on. Where's my mute everybody button? I have the power.
Sorry about that. Thank you, Elizabeth. Brady, I'm going to hop over to you, and then we'll.
All right, there we go. Now I can hear. Now I don't hear anybody, but you can unmute yourselves to talk to me. Please do. All right. Any questions or concerns before we jump back into topical stuff? I learned something interesting in my previous class that met today. If you want to do any drinking tonight, you need to plan ahead. Apparently, Iowa City is closing bars and whatnot, and restaurants that serve alcohol are stopping serving alcohol as of 10 o'clock. So, if you need to get your drink on to handle quarantine, you need to be planful about it in addition to being safe. So, just a heads up to all of you here. All right. So let me pick up then where I left off. I have lecture one here. We were talking about classical test theory and where all of this stuff came from. Let me put up this picture as a reminder. So I will ask you guys at the beginning of each class period, what do you remember from last time? And your answers can be gestures, they can be words, they can be numbers, they can be images, anything that you think of. ASU, yes, Jing. ASU stands for the add shit up model, or the add stuff up if you prefer. Yes, that is my version of what classical test theory stands for. It's the logic by which you can sum or average indicators and have that become an estimate of someone's latent trait. It is, in fact, fitting a measurement model without actually realizing it. And so that's something that we'll talk more about when we get into measurement models, and we'll return back to this. But I wanted to plant the seed that even if you're just adding shit up, you are, in fact, fitting a measurement model that has very strong constraints to it. Other things, let's see, we don't really do latent traits for formative, we do them from reflective, yes. So formative indicators versus reflective, I had a lot of questions in office hours about that as well. The difference is which came first. So all of the models that we're going to talk about this semester are working with reflective indicators. That means there is a trait. So it's trait meaning like capability, ability, um, attitude, like some characteristic of a person that they have that they then that gets manifested in their observed responses to indicators. So indicator meaning item, trial, some piece of behavioral data that we can actually observe. Yeah, 1 second. Let me finish the first question, then we'll get to why total. Um, So if you have a trait and the trait causes the way that you answer the questions, that's a reflective model. They're reflective indicators. And those indicators should be correlated. If indicators measure the same thing, they should relate to each other. And the reason for that relationship is the trait. So it's a disconfirmable pattern of whether or not the correlations among the indicators are consistent with the idea that they measure one thing or more than one thing. In a formative model, it's the opposite. The trait is it's like the sum of the parts, but the whole is greater than the sum of the parts. So it's like you have these indicators and they come together to form this new thing. And this new composite, this formative construct, can then go and predict other stuff. So it's a different type of idea, and the indicators don't have to be correlated. That type of model is not mathematically solvable until you pull in outside information that the trait is supposed to be related to. That's the only way that it's identified. So formative indicator models are a different animal, and that's not something that these measurement models are designed for. Okay, does that answer your question, Kelly? That was your question. I'm staring at your picture, waiting for it to move. Yes, she says. All right, next question. I don't think the expected value of t is y total. I think it's backwards. So the idea is that the sum is your best guess as to what the true score should be, because errors are supposed to average out over time. That's the logic. So your test score or the item indicator sum is your best estimate of the latent trait according to that. All right, so each of these topics, the first lecture here is just designed to sort of introduce you to the class as a whole and what we're going to be talking about. We'll dive a little deeper into each of these things in the coming weeks. So this is just kind of a big picture intro. I also should mention that you'll notice that my slides are packed full of stuff. That is a deliberate choice. I know that it's not ideal for taking notes, but the idea is that I wanted to write enough things down so that you could just sit back and listen as opposed to constantly trying to write down everything that I say. And that's especially important when you get to things like equations and notation, where getting it right is really critical. So I have a lot of information on here. It might be helpful if you're one of those people who likes to take notes to, write it down on paper or a separate document or something like that if the spacing is a problem. But hopefully you're able to just sit and sort of process. I had to I I don't mind if you're doing other things while you're listening. So I'll just be honest with you. There were some folks that were like stretching in my earlier class, working on their flexibility during class. That's fine with me. During the last faculty meeting of the spring, while the dean was talking, I was giving myself a manicure. Not gonna lie, multitasking very efficiently. So if you need to cook yourself some lunch, you need to fold some laundry, you need to file your nails, whatever, it's fine. Just sit and listen because that's hopefully the slides are enough for you to be able to do most of that. So I'm cool with that. All right. Anything else that you remember or want to ask about? Watching the chat window? No, no. Everybody's looking down or looking bored? Okay, onward then. So the three main areas we're going to cover this semester in terms of models: classical test theory, confirmatory factor analysis, and item response theory. Those are the three main types of models. So that was the end of the classical test theory part here. I think we did that slide if I remember correctly. We ended off, I think, on alpha. So spoiler alert, if you have a scale that has a good alpha, that means nothing. Nothing at all. This is something that, especially trained as a psychology student, when I realized this, I was just dumbfounded because every method section insists that you report an alpha for your scale. It means nothing. So I'll get into the specifics as to why that is. But I want you to look at the dates on this slide here. So let me make this bigger so we can see it. There we go. Folks did alpha because they had to. This was before they had computers that would do things like iterative likelihood estimation and would actually execute all of the complicated mathematical theory that people were coming up with. So there are a lot of techniques that were developed because it could be done by hand, and we don't necessarily think that those are the best ways of doing things anymore. Alpha falls into that category. So after classical test theory, our next stop is going to be confirmatory factor analysis or confirmatory factor analysis, emphasis on the confirmatory. So that's the big difference. The idea that you are responsible for specifying which items are supposed to measure which constructs, what constructs they are, in a sense, which items don't measure each construct, and seeing the extent to which the data support your view. So you have a structure that you're testing, and you get evidence back that it's either consistent with that or inconsistent with that. And if it's inconsistent, it tells you why you're wrong, right? So it helps you fix it, which is more important. So the reason that in preparing for this class, I spoke with several of you when I send out an email. What I need you to know to be able to follow what I'm going to say is regression. That's it. If you know what an intercept is and you know what a slope is, we can go from there, because CFA, confirmatory factor analysis or confirmatory factor models, is nothing more than a linear regression model where the latent trait is the factor and the observed indicators are the outcomes. So it looks like this. I have the factor model equation here. It has some unfamiliar terms in it relative to regression, but if you look at the structure of it, y equals some kind of constant because it's not multiplied by anything, plus something times a variable plus error, it is regression. So rather than having beta 0 for an intercept, I'm going to use mu. It's following along with the notation in your textbook, I believe, or others as well. The slope that relates how the latent trait predicts the outcome is lambda, but it's a slope. It's the same thing. And E is the error because the latent trait doesn't perfectly predict the response. It's going to get it wrong to some extent. In terms of the subscripts, I is for item in this class, and S is for subject. So subject is the person or the respondent taking the items. It's from a more classical sort of experimental design kind of set of notation. It kills me because in every other class I teach, I is individual person, and in this class it's item. So what this equation is saying, it's intended to be for a set of items. Items are indicators. Those words are exchangeable. So there's a response to each indicator for each subject that's being predicted by an indicator-specific intercept. So each indicator has its own expected outcome response to the indicator when the factor score is 0, which is the predictor here. And each indicator also gets its own loading, which is a slope for how the trait predicts the outcome. Each person has a factor score. And so factor score has an S because that is a subject characteristic. And this model is saying that it's the same trait that is predicting all of these indicator responses simultaneously. And then the error that's left over is both item specific and subject specific. So in this class, back in the day when I used to write on the board, I vowed never to use notation that involved Greek letters that I couldn't write. So I think the Greek letter that is more common is the one that I call either squiggle 1 or squiggle 2. I'm not entirely sure which one that is, but it's like a system of curls with like an extra curl on the top, and sometimes there's two curls on the top. I call that squiggle 1 and squiggle 2. I believe that's what your textbook uses. I'm not even going to try to draw that reliably, but I can draw an F. So in my world, F is the trait because it stands for factor. So what the true score idea of classical test theory translates into latent factor here in confirmatory factor analysis. So the model says then what kind of dimensionality underlies your items. So this is an example of a model that says there's only one trait. You could also have a model that has 2 traits or 3 traits or whatever it is. But the key idea is that you specify which items go with which traits. You set that up a priori as a testable hypothesis. You also can decide whether or not some of the errors get to be related based on what the content of the items is. It's a linear model. So the same problems that you would see in linear regression, where your slope, I guess is it the slope this way to you guys? I don't know if it's mirror imaging or me or not. A positive slope looks like this, looks like that. This, I don't know which way it is to you guys. This one? Okay, this is a positive slope. All right, my negative is your positive. Got it. So a positive slope don't care, right? It'll just keep going forever and ever in both dimensions. Well, what if you had an ordinal item that you were trying to predict, right? The slope of how the trait predicts that item response shouldn't predict a response that's lower than, say, 1 or a response that's higher than, say, 5, right? Whatever the scale is. But the model don't care. The line will keep going. So this linearity assumption of how the trait predicts the outcome is really designed for items that are continuous and normally distributed. That's almost never. I can't think of any items that would actually look like that. More often than not, items are binary, ordinal, or some other kind of distribution. And so that's why we need other kinds of factor models for the same reason that one type of linear regression doesn't fit all outcomes. One type of factor model doesn't fit all kinds of indicators. It's the same exact problem. The difference between classical test theory and confirmatory factor analysis is that we pay attention to the items, right? The trait is not just the sum of the indicator responses. The trait is this separate predictor variable right here. And explicit in the equation are characteristics of the items, this intercept and slope. So items that have stronger slopes are better items. They're more related to the trait. And an item that has a stronger slope is a better item for everybody. So we're going from all items are created equal to no, items differ from each other in their intercepts and slopes, and that should matter because this trait is a separate property now. Okay, how we doing? Yeah, all right, cool. So again, looking at the dates here, the history of factor analysis, starting from about 1904 onward, folks were trying to figure out how to do factor analyses, and they used various types of matrix decompositions to do so. Those are techniques that are exploratory, we're talking about here. Exploratory techniques are something we're going to spend a little bit of time on the next lecture. It's not all that. It's not as useful. So we get into sort of this treatment in the 1940s, people trying to work on this, then they finally realized that if you're trying to predict items that are not actually continuously distributed or symmetrically and continuously distributed, that this linear factor model is a problem. So they figured out what to do instead, something that's known as item response theory, or what I will call factor analysis on logits, for those of you who've had that. So the history of this goes back to psychophysics and looking at signal detection theory and sort of just noticeable differences. The same types of curves that are used in that work turns out to work pretty well in in characterizing how a continuous latent trait predicts a binary or ordinal response. And so we end up with item response theory as the answer to the slope going out of bounds. So linear regression is predicting a quantitative outcome from a predictor that's observed. Confirmatory factor analysis is predicting quantitative indicators from a latent predictor. If you go to logistic regression, that's predicting a binary or ordinal outcome from an observed predictor. So if we get to this item response theory, that's predicting ordinal or binary indicators from latent predictors. So there's like a 2x2 table here. And so if you've learned logistic regression or multinomial regression, this is going to sound really familiar. The only catch is that it's going to look nothing like it. It looks completely different. You'll see pictures that look like this. Isn't it nice and pretty? Have you seen these sort of pictures before? A few of you have. So this is what's known as an item characteristic curve. It has the abbreviation ICC, which in my other classes stands for interclass correlation, but not in this one. Different ICC. But this is showing the predicted outcome on a probability scale, so it's a binary outcome in this case, for different levels of the latent trait. So the x-axis here is the latent trait, which in the world of IRT is called theta. So that's the one Greek letter I can do pretty reliably, so I kept that one. And this shows that as theta increases, the probability of getting an item right increases. And so if you predict the logit of a binary outcome, and you back translate that predicted logit into probability, you get these curves. The end result is that the slope that relates, this way, the positive slope that relates how a trait predicts an outcome understands that it needs to shut off. It understands that it can't go past 1 and that it can't go past 0. So it's sort of a like walk like an Egyptian sort of curve here because you got the boundaries happening. So yes, for those of you who were not alive in the 80s, after class, ask the Google about the Bengals walk like an Egyptian. It's an excellent music video where people are walking around like this just for no reason. Oh, I miss the Bengals. They were a lot of fun. But anyway, um, in addition to slope and intercept, there are two other properties that show up of items, upper asymptote and lower asymptote, because some items stop short of going all the way to a probability of zero, and some items, sorry, this way, probability of zero, and some items stop short of a probability of one. So we'll spend a bunch of time on these sorts of models because most of the indicators that you will work with in measurement are going to be ordinal in nature or even binary. So this is actually the more appropriate approach for building measurement models. So here's what the equation that it looks like to predict these things. The slope is this A parameter here, and this B parameter is something like an intercept. It's intercept adjacent. It's what's known as a difficulty parameter. Um, this equation, and especially the probability form, looks nothing like a typical regression model, but it turns out that if you do some algebra to rearrange it, it totally is. And so if you express this model, this nonlinear factor model, in a linear regression type of way, that tends to be called item factor analysis instead. It is literally the same thing, just a different way of expressing the model. Historically, there's been different methods of estimation that go with it too. And so if you fit these kinds of models in R, for instance, if you use structural equation modeling software, what it does is this item factor analysis with limited information estimation. MPlus is one of the few programs that I know of that allows SEM types of analyses that have full information instead of limited information. One thing that's different about these types of measurement models is, in addition to paying attention to differences between items, the idea that items are only good for certain kinds of people. So, like if we go back to the picture here, this green item right here, this green item is not meant to measure people who are low on ability. This green item is meant to measure people who are high on ability. So it only shows any differences in the probability of success once you get out here. So this green item is great, but only for certain ranges of the trait. The opposite of true is if you go to like this blue item over here. Here, by the time you have lots of ability, it really doesn't change your probability of success, whereas the lower people are better differentiated. So the nonlinear aspect of this slope means that a good item is only good for some of the people. And so you really, in addition to paying attention to how good an item is, where is it good is the question. And do you want your test to be sensitive across the board? Then you need items at all different levels of the trait. If you want it for only certain ranges, then that changes what kind of items are useful. So it's a different type of approach to instrument and scale construction with this. All right, so that came about in the 50s and 60s, so it's still not really modern by any stretch of the imagination. Um, you may hear IRT models combined with the term Roche model. Have you heard Roche models before? Is that a term? It's kind of a cult, to be honest. It's a very different way of thinking about measurement models. Yes, so the audience agrees with me. Yes, it's kind of a cult. A Roche model is an item response model where they assume that all the slopes are the same. That is my perspective. To other people, the Roche model is the way and the light, and everything else in IRT is voodoo. It's like if your data don't fit the model, you fix your data because this is the model, damn it. Like that's Roche. So I will make you conversant in the vocabulary, but just know that I have the perspective that no, that's just one option, and it's actually not a great option in most cases of items that aren't just like academic items, right? Okay, so putting it together, we have sort of two different families of latent trait models. If you have continuous responses versus responses with some kind of boundary, you can fit these sorts of models though to any kind of outcome. So if you have counts of behaviors, right? So like if you have something like disruptive behavior in children, and you observe them for an afternoon and you count how many times they interrupt their classmates, how many times they try to punch somebody, how many times they try to wreck the room, right? There's all kinds of disruptive behaviors. Those sorts of counts can be indicators of this latent trait. And you would fit a count type regression model where the latent trait is the predictor to be able to do that. And if time permits, I have some examples of outcomes that look like that we can fit trait models to. So, all right, so let me pause for a second, get questions from the audience, reload. Questions or comments so far?
I have a question.
Hit me.
So you were mentioning, maybe I was taking notes and didn't catch this. So for when you're talking about the nonlinear slopes and how it's only good for certain areas,
Hmm.
like certain parts of the trait. So wouldn't the Roche model just eliminate that variability altogether?
No, let me go back to the picture. So of the two properties, one of the properties is where on the trait you are.
Okay. Okay.
That one's still there.
Okay.
This picture under a Roche model would have parallel slopes.
Okay. No, now I get what you mean.
Yeah, so items are equally good.
So it'll
Now,
be kind of just like that green one, except just like moved left or right.
yes, you can move left
But
or
they could
right.
all be green, but you can't move like you can't like. I don't know what the term is. I knew I had a transformation term at some point in my life.
I'll do my tilty slope term.
Yeah, yeah.
Yeah,
Okay.
you can't do this.
Okay.
Yeah.
So this is Andrea now following up.
Please.
So are you saying that the Roche doesn't include discrimination?
Correct. The
Okay.
discrimination parameter is held constant.
Okay, thanks.
There's two different ways to identify the model. One is that discrimination is fixed to 1 and you estimate your factor variance. The other is that your factor variance is 1 and you estimate your discrimination. It's 6 of one, half dozen of the other because it's just a difference in scale. But the key idea is that items are equally good. So if you're measuring a trait of algebra understanding, right? And you have a bunch of algebra problems and you just swap out what numbers they are, right? I'll buy that. All of those items are probably equally good. But if you are trying to measure a trait like depression or anxiety or something like where there's different items, and some of your items might be, I feel sad versus I feel like killing myself, right? Like those items are different. In addition to being different along where they are, how useful they are is likely to be different. So my worldview is that sometimes the items want to have different slopes and they should be allowed to do that if that's what the data wants. That's my personal view. Under a Roche modeling point of view, you would kick out any items whose slopes appeared different than the others. You would refine your data until it fits the model with a capital T. Questions? Oh, discrimination. Yeah, sorry, I'm getting ahead of myself. Discrimination means the slope. So it is the factor loading or the slope of the line. The A parameter in an IRT is the same thing as the lambda slope parameter in a CFA. Yep. Getting ahead of myself. This is what happens when I work on lectures. Like I've been working on the lecture for next week. And so I'm using that terminology as if you guys have already heard it because like that's where my head has been and I forget. So thank you for speaking up. I appreciate that. Okay, other questions? All right. So, where were we? Here, sales pitch. So why should you stick around in this class? Because I know you don't have to, right? This is an elective. For most of you, you're here because you want to be, and I appreciate that because I want to be too. But here's my sales pitch for why this shit matters. So, first and foremost, explicit models for dimensionality. You can have the best intentions when you create a scale or a set of scales to measure something, and you can write the clearest items possible. And you think they measure X and they measure Y, and you could be totally wrong. The problem with older techniques that use exploratory methods is that there is no way to know if you're wrong. You can come up with what you think it looks like, and someone else could come up with what they think it looks like, and you're both right because there's no external criterion. Confirmatory models require you to specify some kind of hypothesized dimensionality, and you can see if you're right. So all of the models that we're going to spend time on are confirmatory in this way. It's not that you have to be right. It's that you have to have an idea to start with. So you can fit a model, see the parts of it that don't work like you thought, change it, and see if it fits better. Now, you should have, in hopefully, more than one sample because some of the changes that you might make would be sample specific and idiosyncratic. So ideally, like you would come to the same conclusion across a series of samples and other people would find it too. But the key idea is that you can test whether you're right. And when reviewer 3 asks you, wait a minute, I think that this construct is not the same as that construct and your scale is measuring both and that's why I reject your paper, you can say, no, I tested that, and here's the evidence for why I believe that I've measured one thing or measured two things. So that's the big one. It also provides a context for selecting which items should be included. Because when you're building instruments, you don't want unnecessary redundancy. Right? You want to measure as many constructs as quickly as possible, and these models that have item parameters that tell you for what kind of person a given item is going to be most useful can help you create targeted, efficient measures. And this is true whether you're measuring math or whether you're measuring depression, right? The same techniques can be used to measure all kinds of stuff. You can provide comparability across persons, items, and occasions. So one of the big problems in longitudinal development, so studies of human development, aging, even young children or adolescents, is that you can't give kids the same test as they grow up and expect the test to work. So if you want to measure reading ability, right? If I gave a reading ability test to my 5-year-old, he would just draw in marker all over it and hand it back to me and be like, look, mommy. But if I tried to measure like pre-reading skills, right? He can recognize most of his letters, right? We're working on that. The video games actually help with that because he wants to write things in the video game and I make him hunt for the keys on the keyboard because to him, QWERTY is just a random set of numbers, right? Like where the hell are these letters? Like they're in no kind of order. So I could measure, pre-reading kinds of skills, and then hopefully next year he'll be able to sound out like 3-letter words and he can pick up, and by the time he gets to high school, I can be giving him extended passages and asking him questions about comprehension. But if I want to measure the same trait, I'm going to have to change the way that I measure it. But if you want to measure how reading grows, you need measures that are comparable. So if a reading score is nothing more than the sum of the items, you'd have to give the exact same items every single age you measured it at. Deal breaker. Doesn't work. Instead, with latent trait models, and this is usually touted as a benefit of IRT specifically, but any latent trait model that has a separate estimate of a trait from just the sum of the items falls under this category. So CFA falls under this as well. You can, through careful design of item overlap, create a trait that grows over time with an instrument that grows over time. So if I have items 1 to 5 that are the easiest items on a scale, I give that the first occasion. The next occasion, I give items 3, 4, 5, but I add 6 and 7. The next time, I have 5, 6, 7, and I pick up 8, 9. Right? By the time I'm done, I could be on item 200, have none of the original items, but still have a trait that's connected. That's known as vertical scaling or vertical equating. It's common in situations in which you need to change the instrument over time. If you have overlap, it can be done. If you just abruptly switch measures, you are screwed. So being planful about changing measures is essential. I can't tell you how many times I've had people ask me, well, I gave measure A at the first occasion, and then I gave measure B at the second occasion, and I want to measure change. And I'm like, nope, you have created a confound. You really have to believe that A and B are measuring the same thing in the same way, and you have no evidence of that. So carefully is the thing here, but you can get scales that change. to examine comparability across groups. So, if I wanted to measure how depression manifested itself in teenagers who were boys versus girls, or teenagers who were like 17, 18, 19 versus 13, 14, 15, right? I have to be able to say that the items are working the same way in measuring depression. That's an empirical question. So that's what's known as measurement invariance or factorial invariance when it's done in a confirmatory factor analysis framework. It is known as differential item functioning in an IRT or IFA context. And note that the wording is backwards. The wording on this is absolutely horrific, by the way. Like, whoever made this should just be drug out and shot because it is the worst. Do you know what you say if something is the same? You say that it is invariant. Do you know what you say if something is different? Non-invariant. Yeah, non-invariant. I'm not making this up, I swear. So the term differential item functioning is the same as measurement non-invariance. Seriously. But the idea of testing whether or not the way the items relate to the trait is the same across groups over time or as a function of whatever covariates, that's the idea of invariance, and we're going to do that too. Internal and external evidence for construct validity, I'll say more about that next time. And you can also mix and match. So another problem with classical test theory type approaches where you just add shit up is that each of the items has to have the same possible distribution. Otherwise, items that have more variance are going to be more heavily weighted. But not all items lend themselves to the same response format. Some constructs, like some aspects of a construct, like you can just ask, do you agree with this, yes or no? And other things you need more gradation. There is no rule that all items have to be the same in order to measure the same trait. You can combine things like response times, things like accuracy, things like attitudes. Like this is a process measurement. So I'm giving you a shout out, Minchin. She was talking about this the other day. You can have all different kinds of indicators and mix and match and have them all measure the same kind of trait. You don't have to stick to the same family of outcomes. So you have total flexibility within this framework. So how's that for a sales pitch? Are we excited? Some of you look excited. Okay, yellow thumbs. Clapping. Oh, thank you. Yes, I'll take yellow thumbs. I know it's like 2:45 in the afternoon, and it's sort of like the excited is not usually part of my vocabulary at 2:45 in the afternoon. So I'm trying to be sensitive to that, but it will be worth your time. I can almost guarantee it. At least I believe that in my heart of hearts. So what are the downsides? Sample size. Um, Several of you may be from research areas where you would consider a large sample to be 50 people. Anyone fall into that category? Show of hands. Not in this group? Okay, well, you're lucky then, because a lot of my previous students have worked with special populations or hard to measure folks. In particular, studies that use neuroimaging, they might have like 15 people. And the bad news is that a lot of these techniques are what's known as large sample techniques. You're not going to be able to do all this cool stuff if you've only got 15 people. What you can do is add shit up. You can always add shit up. And so that's part of the reason why these techniques, the older techniques, have stayed around. So some of the fixes that you have learned about in other stats classes for small samples are not a thing in these models. So for instance, if you're fitting growth curve models or multi-level models on small samples, you can change your method of estimation from regular flavor maximum likelihood to something known as residual maximum likelihood that's less biased in small samples. REML is not a thing in any of the models that I'm going to talk about. It's not even programmed into structural equation modeling software. Neither is denominator degrees of freedom. So every test that you're going to see is going to be some kind of z or chi-square that ignores sample size. So these techniques are not really designed for smaller samples. The very last week of class, I'm going to give you some workarounds. That's a lot of current research, is sort of figuring out, okay, if you can't do it the best way, what can you do instead and still try to remain faithful to the data, especially in smaller samples. Estimation is harder. Things to read are often harder, except for the stuff that I picked. So some of this stuff can be somewhat intimidating to capture, but I'm going to try and help you as best I can. And then last but not least, some people think that SEM is going to fix their data. It will not. So if you have items that are terrible, they're still going to be terrible if you fit a structural equation model to them. You'll just get more evidence of their terribleness. You'll get a more precise estimate of just how shitty they are. That's what you will get. The other term that gets used in terms of structural equation modeling is causal modeling. Nope, absolutely not. The word cause will be nowhere in our vocabulary this semester. What we have is a pile of covariances, and we're going to put a bunch of arrows between them and say this relates to that and this predicts that, and that's what it is. There's no cause involved. So causal inference, to answer the question that just came in, is from design. Causal inference is always from design, not statistics. So if you have a design that supports causal inference, then you can make that inference whether you're doing a t-test or a structural equation model. But I am not assuming any kind of causal inference is possible in any of the examples that I give. Question from the audience. Let's see here. Good questions. Thank you. Um, you can only do cause if it comes from the design. And I don't think of it as a yes, no, I think of it as a spectrum, right? Like people would say things like smoking causes cancer. Do you believe that? Smoking is bad for you? I think it's bad for you. But can I say it's caused it? Ugh, ugh. That it makes me uncomfortable to go all the way to the other side, because unless you've taken a pair of same-sex identical twins and randomly assigned one of them to become a smoker and the other not, right? Like that's the level that you would have to be able to rule out all possible external explanations. So most of the time, the kind of data that people fit SEMs to, and by the way, don't ever say SEM model. Just I'm going to pause a minute, but you think about why that's bad. SEM model is like ATM machine. Okay, model is the third letter. So if you say SEM model, that is a dead giveaway that you don't know what you're talking about. So you will know that I am really tired if you hear me say SEM model. Like that is a sign that like all systems have shut down for the day. So people fit SEMs to correlational data. They grab a sample of people, they give them a giant questionnaire filled with 8,000 questions measuring 10,000 constructs, and then they try to fit some sort of a model that shows what constructs are related to what and how the items relate to the constructs. Like that's the most typical type of SEM application. If you are in a situation where you have a controlled experiment, right? You have random assignment, you have elimination of alternative explanations, you have, what's the other one? Manipulation, right? If you have those things, then you may have a better shot at some kind of towards the causal end of the spectrum than other people. But it's not causal modeling just because you got M plus out to do your analysis. Doesn't work that way. So, all right, next question, DCMs. Okay, so I'm thinking of like a three-way table in my head in terms of types of variables, types of traits. So if we just stay within the world of measurement models for right now. So in latent trait measurement models, the trait is the predictor and it is latent, meaning it is not observed, right? It's a thing you believe exists, but the only way that you've measured it is through observed variables, and so that requires some sort of belief structure there. If you have a continuous trait, it's usually normally distributed in almost all cases is the assumption, or multivariate normal for multiple traits. And that trait predicts continuous responses. That is a CFA model, confirmatory factor analysis. If you have a continuous normally distributed trait that predicts binary, ordinal, or nominal responses, categorical data broadly construed, that is IRT, item response theory, or item factor analysis. If you have a continuous latent trait that predicts, say, a count variable or a zero inflated count or like a gamma, something that's continuous and skewed, that doesn't have a name, but you can still do it. I would call that generalized SEM, maybe, because it's like other generalized models besides ones that have names. Okay, so with me so far on the categories? And we're going to do all those models this semester. What I don't have time to do is question about DCMs, so diagnostic classification models, otherwise known as cognitive diagnosis models, special cases of which all the acronyms DINA, DINO, NIDO, LCDM, there's probably others, right? So all of those letters that I just said, the big difference is that in those models, the latent trait is a category. It is an attribute, is what it's called, rather than a trait. So those models are used, or sorry, I forgot the other half. The latent trait is a category, and the response typically is categorical as well, but it could be continuous. So there's nothing that says you can't fit a DCM on continuous responses. That's just, I think, either a less common or hasn't been done yet. But it's the trait that's the big difference. So I have a slide on this somewhere. I'm probably getting ahead of myself, but I like answering your questions better anyway. This is more fun. The reason that you would fit those kinds of models, there's two reasons. One is that you believe in your heart of hearts that it is a categorical trait. Like either I know how to do this algebra type of algebra or not, right? I have learned how to FOIL, for instance. And you can give me 10 problems, and if I have learned how to FOIL, I am more likely to get all of them right than not right. And someone who hasn't learned how to FOIL is more likely to get them wrong, right? If you believe in your heart of hearts that there's just like an on-off switch on your trait, it's not a continuum. It's just you have it or you don't. That's what those models are designed for. More common is using those models in situations in which you think your traits actually should be continuous, but you just don't have enough information. So you are forced to categorize your trait conceptually because that's the kind of information you need coming out on the back end. So for instance, if you want to know whether a student should be classified as proficient at math, right? End of grade tests, people report levels of proficiency as a category. Now, in reality, your students vary continuously in their abilities, but for purposes of reporting, you need to classify them as proficient or not. Well, if what you need to do is classify them, just start with the model like that. You would fit a latent attribute that says proficient or not. That's your new predictor of your indicators that are usually binary or ordinal in that case. That's what DCMs are for. So in situations where you're going to need to make some kind of cutoff anyway, just start that way with the trait. Okay, long-winded answer. Does that, let's see, I'm like 2 questions behind. So does that work for DCMs? Waiting for the thumbs up or the response.
Yes.
Yes, okay, cool. Next, regarding bad items, can we eliminate bad items after analysis? Yes and no. So how bad is it, is the question. It's very fun in this class to see people's real data and to see when things work or don't work. And I have seen some spectacular cases of items that were supposed to measure something that just didn't work. So to give you an example of how bad is bad, right, I told you that this is the positive slope, right? I got it right this time? What if I had a slope that went this way instead? A negative slope. That you were more likely to get the item wrong as your trait increased. That's a bad item, right? That's bad. So there's something wrong there. That arguably that item should go no matter what. But if it's not supposed to be reversed, you shouldn't flip it around. So if it wasn't supposed to be reversed and that's what you found, that's a bad item. Now, the other ways that items can look bad is when you only pay attention to how correlated they are with other traits. So if you have an item, let's say that 10% of your sample gets correct. Is that a bad item? Well, some folks would say yeah, because it doesn't show a lot of variability. It's really extreme. You don't need it. But an item that only 10% of the people get correct is designed to distinguish people of really high abilities from one another. That's where that item is good. So it's not a black and white, is the item good or not? It's where is it good? If the item has a negative slope, it's not good for anybody and you don't need it. But otherwise, if it's good in an area that you don't have, even if the slope is not strong, it's still better to keep it in. But yeah, you'll get a lot more information about your items, and you can use that information to decide whether or not to keep them. Where this comes in handy is if you're trying to create, say, a short form. Let's say you know of an inventory that has 50 items. You don't have time to give all 50. You'd like to give 10, right? You'd like to give 10 but not lose any information. Well, the item statistics that come out of these analyses give you data with which to say which 10 they should be to try and maximize still your coverage of the trait but not have redundancy. So things like that. All right. Other questions? All right, what's next then? Oh, switching gears. Okay, so going through just a few examples of the kinds of things that we'll be talking about, a little bit about item and instrument development because it differs in terms of what's good strategy when you're thinking about adding shit up versus when you're thinking about fitting a measurement model. So two examples that we'll have here, teachers measuring math, psychologists measuring depression, trying to hit all of my bases in terms of the programs that you guys are coming from. Common denominator is that we're trying to talk about latent traits. So underlying variables, unobserved, continuous in nature. That's what we're trying to do. So let's say that we have a math teacher. They give 20 items. The items are scored such that you're either correct or not, so there's no partial credit. It's a math test that's supposed to cover both algebra and geometry. Okay, could happen. If you sum the number of items correct and say that's your test score, what can you then do with that information? So first question would be, well, am I measuring one thing or two? I just said the test measures algebra and geometry. Is it possible to be good at geometry but not algebra? Is it possible to be good at algebra but not geometry? Now, they're hierarchical, so I would think that if you're good at geometry, you've probably got algebra down. But just because you've got algebra down doesn't mean you have geometry, right? Point being, they could be two different things. So if you have a test that measures two things, that's tricky because you could be good at one and not good at the other, or average on both, and you'd end up with the same type of score. If the one score is sufficient, how accurate is that score? And so what is important to consider in addition to someone's score is the range around their score that the scale unreliability would predict. So each person gets a score, but you know that if you gave them multiple measures over and over again, the score would wiggle a little bit, right? Like how big is that wiggle? And does that change how you would then use the scores in practice? If you decided to have 10 items each, how much lower precision would each of those scores be if they came from 10 items versus 20? Depends on how the test was put together. So how many items do we need? How few can we get away with? That's always a concern. Are there other ways of getting the right answer? So if you changed from let's say it was a multiple choice test, right? If all the distractors are not equally good, then some items have a higher probability of being correct by chance. You want to be able to take that into account in the model and allow that to happen and watch for that to happen as a potential way to screen out bad items, right? Or to improve your distractors. Could you create more than one test? So test security is always a big issue. If you give out the same test, maybe kids are going to find it, copy it, steal the answers, and so forth. Like, can you make another test, but is it equally difficult? Because you always want to be fair. Test scores, test floors, test ceilings. Do you know these terms? They're pretty common use. Test floor, everybody does really bad. Test ceiling, everybody does really good. Those are often talked about as undesirable qualities, but not necessarily. Do you know what kind of distribution of grades I hope this class has? Degenerate. Do you know what a degenerate distribution is? It's one that has no variance whatsoever. I want a ceiling. I want just a pile of A pluses. That is what I want for you, right? I want a giant ceiling effect. I would feel really good about myself if you guys demonstrated that level of mastery, and everybody did that, right? If you are trying to predict who is capable of going on to further study, for instance, from a test, and everybody's at the ceiling, you've got no information with which to predict who might be more able to continue on, right? So in that case, the ceiling would not be good. So it depends on what you're trying to do. Are the items free from bias? Are there other reasons why people could get it right that have to do with things that you're not interested in measuring? So that's always an issue. So changing gears, psychology. Items measuring traits like depression, anxiety are often asking you to how much you agree with certain types of statements. And so the statements are designed to elicit a range of responses, even though each statement usually has a range of options. So things like depression. One of the signs of depression is supposed to be that you don't have a lot of energy. So if you have an item, I have lots of energy, and rarely to almost always, somebody who is higher on depression should answer more like rarely. Or I feel sad. Well, I think sad is the normal part of life, even if you're not depressed, right? Sometimes people feel sad. So that would be an item that everybody could agree with. It would pick up on a really low level of depression or arguably none. Crying. That's another one, but that's one that we might have to worry about in terms of possible differences in personality, gender, socialization, culture, things that make crying more acceptable to some kinds of people than others, right? Or I think about ending my life. Now, these are real type items from measures. Suicidal tendencies or thoughts, right? That's the hallmark of depression. But you have to be pretty bad off before you'd say anything other than rarely. Now, if we think about fitting an ASU type model here, let's reverse I have lots of energy because that's going the wrong way, and then we add shit up, right? Do you think all of these items should be weighted equally? Yeah, me neither. So if someone said, I almost always think about ending my life, that's a bigger deal than if they say, I almost always feel sad. So we need some way of placing these items on a continuum where all almost alwayses are not equal. Um, Other things that might be relevant in terms of I have lots of energy. If you give this scale to younger adults versus older adults may say that they lack energy for reasons that have nothing to do with depression. So that item maybe isn't useful for older adults. And so when you're fitting models, you can choose to not include all of the items for all of the people. If you have a reason, theoretically, why things are not relevant in certain types of people than others. Um, Incidentally, the original item here, I feel sad, I had written, I sometimes feel sad, because you will see items like that, even though the response scale is rarely to almost always. You will see a sometimes written in there to hedge it. And so then you have to think to myself, if you say, rarely do I sometimes feel sad, that could be because I always feel sad. So it's rare that I sometimes feel sad. So watch out for those kinds of items. Yeah, we hit all that. So dimensionality, accuracy, efficiency, these are all sorts of the concerns that we use latent trait measurement models to address. Generalizability in terms of looking at how these scales function across groups, that's invariance and differential item functioning. Where are we at? Almost done. Okay. So there is a book that I would recommend if anybody is in the process of building new instruments, like if you want to create a measure for a dissertation or something. It's Constructing Measures. It's Mark Wilson's book from 2005. I used to own a copy of it, but some student borrowed it and never gave it back like a million years ago. That happens to me a lot, and I haven't rebought it, but I think it's worth the investment. And so I've stolen some material out of that book that I liked in the way that he characterizes these things. So it's the idea of what all do you have to think about when you're designing a new measure? Like where do you start? Um, you have to find a way to consistently summarize responses that people make. So what should you ask them and how should you ask it? Measurement is the process of assigning numbers to attributes, but there's a lot of different steps and considerations that you take in before doing that. So we're starting from the assumption that we need to measure at least each trait well, right? You can have an instrument that measures more than one trait, but we have to demonstrate that each trait can kind of stand on your own. So when you're thinking about how to create a measure, he wants you to focus on each of the traits separately and think about one of those. There's a recent article that I added to your list here. The Tay and Jeb piece is one of the first ones that I've seen that actually focused on polarity of your trait. So whether or not if you are high on your trait, what is the opposite of high? Is it just like the absence of the trait, or is it all the way in the other direction? So if I have a trait that's measuring something like happiness, is the low point of the scale just the lack of happiness? I think that's what, anhedonia? Is that a word? Any psychologists in the house? That sound right? Yeah, close enough? Okay, I'll be the psychologist today. Yeah. Like, is lack of happiness the lowest that you can have, or does it go all the way to the other end and get to sadness? Because then you run into potential problems of there really being two different traits. And so thinking carefully about whether you want to have something that's in one direction where the low point is the absence of it versus heading all the way into the other direction is important. So I just mentioned this. Yeah, I knew I had this in here. If you're thinking of your trait as types of people, then these aren't the models for you. Those are diagnostic classification models or cognitive diagnosis type models. So they're not types. But within each of your latent traits, you should be able to conceptualize an ordering of persons. Like, what would someone look like who's low on this trait, and what would they look like if they're high? And then, what kind of items would be suitable for each kind of person to respond to? So, what kind of item would differentiate amongst low people? What would they be able to do with reasonable success? What would be too high for them? What would be too low? Like, you should be able to think about items and persons as being on the same continuum. And he has this idea that he called a construct map. I will apologize for the quality of this reproduction, but this is like a scan from like 2007 that I blew up. So his construct map here has uh, X is the construct here from up to down, respondents are on the left, and items are on the right. So he has it in sort of a generic focus here. I used to have students make me one of those as one of their homework assignments, and so I asked a few that I liked to borrow them, and so I wanted to give you some of those. So this is an example from a student who was in the communication disorders and speech language type program. This is at the University of Nebraska, and she mapped out speech sound development. And her idea of like what kind of person would be low or high is that it was very much age graded. And then on the item side, what kinds of speech sounds a person of that corresponding ability would be able to say. And she actually had different predictions for both boys and girls, which I thought was interesting. So just to highlight one of these here, the TH sound, that one doesn't come in until age 8, which is a relief because my 5-year-old seems perfectly normal. He does not have a TH sound yet. It's still F. So he says things like happy birthday and 1, 2, 3, 4, 5 when he counts. So he's somewhere down here in terms of the speech sounds that he's been able to master. Here's another one. This is for standardized interviewing in another language. And so this is about second language learners, sort of, this is the people side. what you would expect of somebody of lower versus medium versus higher levels of the traits. And these are the kinds of items that you could give them to do where they would match that level of proficiency. So thinking about this can help you try to figure out what kinds of items, in theory, would go with people of different kinds of abilities. And if you want to measure people well, you have to know which kind of people you can measure well, right? And so having items that are super easy, super low, and items that are super hard is the only way to make sure that your measurement scale extends into as far as the traits as you're going to. So I think that's a good place to pause for a moment here. So questions and comments before we adjourn. I'm almost out of soda, so that's how I know that it's time to go. All right. Is there anyone who's actually in the process of doing scale development work right now? Let me ask you that. Yes? One person? Tell us about it.
So I was working on a scale with my advisor, and we are trying to develop the scale to detect social functioning ability.
Social functioning ability?
Yeah, so it's kind of based on the ASD population, but it's a new, more general concept construct, and we are actually facing some problems because there are some similar scales being used in the psychological domain, and we are trying to parallel our scale with other scales, but just like based on our data, we have some like discrepancy. So.
Okay, so your name is Shiyun? Is that
Um,
close? Okay, good. I'm gonna call on you then
okay.
for real life interjections. So
Okay.
here's a quick question. If there's already scales out there that do this, why did you make a new one?
Um, so we're for other scales, they are actually trying to measuring different parts of the autism behaviors. So all of other like already established scales, they measures all the dimensions. Let's say that way. We are just trying to measure just one dimension, but and also because like for other scales they are mainly used by psychologists or clinical psychologists that trying to um, diagnose whether the children or like people has ASDs. But for our construct, it's like we're trying to do it on a spectrum, so it both covers normal functioning people and ASD, so it's kind of different.
Okay, so it's more specific and designed for a slightly different population. Would that
Mhm.
be fair to say? Okay, great. That will make an excellent example to continue with next time. So, all right, folks, it is Thursday, which means have a great weekend. Stay healthy, stay safe, and I will see you next week. So, deuces. Peace out.